Hello guys, welcome to this review session. The first thing that you can see here is the Ethernet frame fields. What are the fields in Ethernet frame? From left to right, we have preamble, SFD, start frame delimiter, then we have destination MAC address, then we have source MAC address, then we have length or type, 2 bytes, then data and path if needed, and the last frame field, which is frame check sequence FCS for 4 bytes. Size wise, we have preamble for 7 bytes, just 1 byte for SFT start frame delimiter. Destination MAC and destination and source MAC addresses, they are each 6 bytes. 6 times 8, 48 bits. Then we have 2 bytes for length or type. Data and path can be from 46 up until 1500 and 4 bytes for FCS. One thing you need to remember is the transmission order. It is from left to right, so it's from preamble up until FCS from left to right, and it is in serial bits. Let's start with preamble, 7 bytes length. It is in fact altering pattern of ones and zeros for 7 bytes, and then we tell the receiving station that the frame is coming. In other words, preamble provides a means for synchronization. Next frame field is SFT start frame delimited just 1 byte, and SFT indicates the next bit is the leftmost bit in destination address. In other words, the next bit is the leftmost bit in leftmost byte of destination address. So it indicates the beginning of destination address frame field. Then we have length or type frame field depending on the version of Ethernet. So we have length when it indicates number of client data bytes that are contained within the data field of Ethernet frame. Or it can indicate type of payload carried by the frame itself if we are using Ethernet 2 variation. Remember that either way, the length for this frame field is 2 bytes. Then we have data and path, and then FCS frame check sequence. It contains 32-bit CRC value. So CRC stands for cyclic redundancy check. 32-bit CRC value is inside FCS frame. And when the receiving side receives the frame, it is going to recalculate CRC, and if the new CRC matches the one inside FCS frame, then there was no change in transit with that frame. Otherwise, we can say that the frame got tampered with in transit, and that's why the receiving side discards the frame. FCS is generated over destination address, source address, length field, and data frame field. So 4 fields are involved in FCS generation. and this is called FCS generation span, these four frame fills together. So it starts after SFT, so it does not include SFT. Starts with destination address, source, and then source address, and then length or type, and then the data. These four frame fills together form the span for FCS generation. And when we want to put CRC value inside FCS, however, remember we consider the last frame field FCS itself as well. So FCS error detection coverage also includes FCS or also covers FCS. So error detection, 5 frame fields are covered, but FCS generation, 4 frame fields are covered. Now, in the next step, I would like to talk about forwarding process. We have 4 different basic switching functions, and you need to know and understand them very well. The first one is just forwarding. The second one is filtering. If we have unknown unicast, we're going to flood it again, and if we have broadcast frame, we're going to flood it. Let's start with forwarding frame. Forwarding process is when destination address is found in CAM, content addressable memory table, or MAC address table. If we can find a match inside CAM table for destination address, then what the switch does is in fact to send that frame out the port associated with destination address in the CAM table. This is basic forwarding process of a switch. If the port associated with destination MAC address of the frame is equal to the port originally the frame came in on, then the second process, filtering process, is going to happen. And that means we're going to ignore that frame because we cannot send the frame out the interface on which we have received previously that frame. And that means that we're going to ignore it or discard it. If we don't know or if we cannot find any matches for the destination MAC address of the frame inside our CAM table, which is known as unknown unicast, because the destination MAC address is unknown to the CAM table, then we're going to do flooding. It means that we're going to send that frame out of every port of the switch except the one on which we have received it. So you can see that it's still split. And the fourth one, or the fourth type of switching or basic switching function, is flooding when we receive a broadcast frame. Of course, the name broadcast implies that we need to broadcast it, so we flood it. Similarly to unknown unicast, we flood broadcast frames out of every port of switch except the one on which it was received. If you have noticed, this frame by frame decision making process or frame by frame behavior of the switch to decide on the forwarding method, be it forwarding, flooding, or filtering, it is going to be cumbersome if you want to do it in port-based scale for each port, so frame per port. That's why we would like to do some sort of grouping here. So we group some ports together and we call them VLANs or virtual LANs. In other words, as I always say to my students, we get a virtual saw to cut a physical LAN into a couple of virtual LANs or VLANs or sub LANs, let's call them, but virtually, yeah, not with steel blade. In this way, we're hoping to put some logic inside the switch, and we do that instead of the default frame by frame behavior to choose which port or which ports exchange data. We do that to group some ports together and we decide on group of ports per VLAN scale instead of single port per frame. In other words, instead of per frame decision making, or better to say per frame per port decision making, uh, we try to do per VLAN decision making. So we make decisions for a group of ports instead of a single port. Each of these groups or each port groups is in fact a single VLAN, or in other words, each group or port group is an individual LAN segment, and that individual LAN segment implies another concept. That means that each VLAN or each port group is in fact a single broadcast domain. So we can see that not only routers can break the broadcast domains, but also VLANs in switches, they can also break broadcast domains, and each VLAN is a different broadcast domain than other VLANs. That simply means that we help with the performance because we reduce the span on which a broadcast frame can traverse if we use VLANs. Next stop is spanning tree protocol. Remember to add redundancy. For physical redundancy, we add more equipment. Let's say we add extra switch to our LAN in case the first one goes down and the second one can take over. But that results in physical loop or simply loops, and we need to avoid loops because otherwise flooded frames are passed between switches in the same VLAN forever. So if you consider one VLAN spanning between 3 or 4 or 5 switches, then for a flooded frame, we're going to pass down traffic between all those switches in the same VLAN forever. We need to stop that. Otherwise, that traffic on its own is going to overutilize our links, our infrastructure. To break that loop, we use spanning tree protocol by which we're going to elect a root bridge or a switch. One switch, which is called root bridge, is chosen, and other switches measure their distance from root switch. When they measure their distance from root bridge or that switch, that specific switch, if they come across more than one way in order to get to root bridge, if more than one way to get to root bridge, then that simply means we got a loop in our network. And that's why we need to block some ports to break that loop. And this is exactly where SCP Spanning Tree Protocol enters. It is defined under IEEE 802.1.1d in order to identify and temporarily block loops in a network segment or VLAN. Remember, SCP, as the nature of it suggests, needs to be dynamic. It is a dynamic protocol. And here by dynamic, what we mean is that in fact SCP actively monitors all those paths, and in case we have a link failure, and that means that, let's say, the main path fails, then it is going to dynamically and automatically change the blocked ports or the ports in blocking mode to forwarding mode, so that it can switch to a secondary path in order to forward traffic. So a block port can be changed to a forwarding port in case of failure, thanks to STP being dynamic. Next stop is trunking. A switch port is normally assigned to a single VLAN. But as I mentioned earlier, we can have different scenarios, and in fact, this is very common when we have a VLAN spanning between different switches and in different physical locations. So we can have a VLAN for, let's say, sales department of a company, and sales department itself is spanning in different floors of a building or a couple of buildings between different switches. So how the traffic for that specific VLAN can pass between all those switches? The answer is by having a trunk port instead of an access port. So trunking allows multiple VLANs to function independently across multiple switches. That's the main idea. A port on a switch, as I said, normally belongs to only one VLAN, and any traffic received or sent on that specific port is assumed to belong to the configured VLAN for that port. A trunk port, however, is a port that can be configured in order to send and receive traffic for many VLANs. For many VLANs. Remember, routers and servers, well, they can also use trunking. It's not only switches. And if a server, let's say, if it uses trunking, that means that that server is allowed to live simultaneously on multiple VLANs, and that is handy in some scenarios as well. So the takeaway point for you is that the trunk port can carry traffic for many VLANs. And how is that possible? That is possible by tagging process. And tagging process is a process by means of which we attach VLAN information to each frame, and we tell the receiver this specific frame is belonging to this specific VLAN, for instance. So by attaching VLAN information to each frame, known as tagging process, trunk ports are able to carry traffic for many VLANs. Next stop is port channels, or what we know as either channels. Either channel is a technique that is used when we have multiple connections to the same device, then we use either channel or port channel. Remember that when we have multiple connections between devices, parallel connections uh, means that we can have loops, and that means that spanning tree needs to be there in order to block all of the parallel connections between devices to avoid loops. But when we have port channels, also known as either channels, the story is different because port channels run underneath spanning tree protocols. Port channels run underneath STP, and therefore STP thinks all the ports within a given port channel, either channel, are only a single port. So STP treats them as only a single port. So once more, either channel or port channels is a mechanism by means of which we group together multiple connections that go to the same device so that they can all work as one unit. And as such, port channels provide distribution of traffic across all those multiple connection or parallel connections, all those links. And this is secondly a mechanism that provides redundancy for us in case of a failure happens. Having parallel connections between devices causes loops, and spanning tree protocol is there to avoid this situation. But it is fine with port channels because port channels they run underneath a spanning tree, so that spanning tree thinks all port channels or let's say all the ports within a given port channel, they're all uh, part of a same single port, or sees them all as only single port. Next up is MLS or multi-layer switching. Uh, MLS, the term itself, is becoming a legacy, and this is due to the wide support of layer 3 switches. So we have MLS to forward frames, not only based on layer 2, but also based on layer 3 and layer 4 headers. When we have MLS, that simply means the switches, they can route as well as switch frames at wide rate speeds using specialized hardware. So in other words, with MLS, it bundles routing function into switches and adds that to switching function. MLS therefore is very useful for core of the network whereby inter-VLAN routing, for instance, can happen. A good question now to be asked is that if that's the difference, then how come that we still have routers, layer 3 devices? You need to bear in mind that having said that, layer 3 is called routing, and the purpose is fulfilled by routers, not switches, because it's in fact the role of routers to break down the network into smaller broadcast domains, and this is not a job for switches. Of course, with routers breaking down uh, a large broadcast domain into several smaller broadcast domains, this disadvantage is speed, because switching is known to be always faster than routing. But as networks grow larger and larger, some systems can be bothered by the amount of multicast and broadcast level that we have on the network, and therefore large networks they usually get segmented into smaller networks thanks to routers. Remember that simply if you consider internet network, then if internet was a switched network instead of a routed network, then just imagine at the level of broadcast and multicast what will happen to the link utilization. Having said that, the most important aspect of MLS multi-layer switching is uh, recognizing the fact that switches they can also route as well as switch frames at wire rate speeds utilizing specialized hardware, and this effectively bundles the routing function into the switch and is specifically useful for routing between VLANs, inter-VLAN routing inside the core of the network. Next up, I would like to talk about network design fundamentals. We know about Cisco's hierarchical network design with three tiers, core distribution access, and also the collapsed core consisting of core and distribution together as one tier, and the second tier that is the access layer. No matter which one, the design is in layers. And designing networks in layers has certain advantages. It gives us the focus. We can focus at different layers. At the same time, different layers can build on each other. At the end of the day, it's in fact the layers that are divided into specific functions. We see shortly the categorization for different functions within core distribution and access. But the main takeaway point here is that this layered architecture provides for modularity and flexibility of our design. And that means our design can scale and can grow later. So categorization uh, into core distribution access layers makes it possible to have modular and flexible, scalable and growable design. In short, core layer is deemed to have high-speed switching. Distribution layer is where we implement policy-based connectivity, and access layer is where we define local or remote workgroup access. Let's see core layer in more details. Core layer is also referred to as backbone because it binds together all elements of campus architecture so that components like WAN or like data center, they are all can be bound together thanks to core or backbone layer. Core layer is expected to have certain core routing capabilities, and also it needs to provide high level of availability. We expect core layer to adapt to changes very quickly. So to ensure high level of availability and also the capability to adapt to changes quickly, we need to make sure that we have appropriate level of redundancy in place to allow for near immediate data flow recovery in case of any failure. So in the event of the failure of any component like node or like a link, we would like to recover very fast. That simply means that we need to have failover plan and equipment. Core layer is also needed to be resilient. And resiliency here means that we need to permit the occasional but necessary hardware and software upgrade or any other similar changes to be made without disrupting networked applications. So this is resiliency in this context. Core layer amongst the three is the simplest yet most critical part. Core layer must operate as a non-stop service. It must be an always available service, in other words, which is required to have 100% uptime. And when we say core layer must operate as a non-stop service, that means or that implies that the minimal control plane configuration that is combined with highly available devices are needed to provide for a non-stop service. Speaking of simplicity of the core layer, bear in mind that core layer should not implement any complex policy services therefore, because it's deemed to be the simplest layer. That's why we don't need to define any complexity there. And an example of that is that we don't define or implement any complex policy. Nor should it have any directly connected user or any directly connected server. Remember, we want core layer in its simplest form. Having said that, because it's a layer that in fact binds together all elements, we want core layer to be able to switch packets as fast as possible. So high speed switching is needed in the core of the network architecture. So to sum up, I can say that high availability was the repeated terms when I was describing the features for core layer, and that's why we need to leverage Cisco platforms that support hardware redundancy, such as Catalyst switches 4500 and 6800 series. Next up is the distribution layer. Distribution layer is supposed to aggregate access layer switches and access layer wiring closets, floors, and also other physical domains that we have with access layer. They are all aggregated into distribution layer. And for that, distribution layer uses a module or layer 3 device like multi-layer switch. That's why distribution layers sometimes may aggregate WAN connections at the edge of campus. But generally, a distribution layer terminates a layer 2 domain of a VLAN, and then distribution layer is the place where routing happens for routing traffic from terminated layer 2 VLANs to other VLANs and also to the core. So once more, Distribution layer routes traffic from terminated VLANs to other VLANs and to the core. Distribution layer is the place where policy-based connectivity is implemented and defined. And when we say policy-based, what we mean is, in fact, traffic filtering or quality of service calls and also security. They all have implication on policy-based connectivity. Availability similar to core layer is important for distribution layer, and availability here is realized through layer 3 redundant paths from distribution to core, and either layer 2 or layer 3 redundant paths from access to distribution layer. In distribution layer, again similar to core layer, fast path recovery is intended. Uh, Distribution layer is also the place where load balancing or equal cost load sharing happens by interconnecting core and access layer via at least dual paths, so that 50% of traffic can go on route A and another 50% can go on route B. So fast path recovery, equal cost load balancing, and quality of service, they are all realized in distribution layer. Another important aspect that has to do with routing is the fact that routing performance can be improved in distribution layer thanks to the summarization. So to improve routing protocol performance further, distribution layer is generally designed to summarize routes from access layer. Very last point here for distribution layer, remember that optionally this layer provides default gateway redundancy by using first hop redundancy protocol FHRP, such as HSRP, hot standby router protocol HSRP, and then GLBP, gateway load balancing protocol, and VRRP, virtual router redundancy protocol. So it is in fact this distribution layer that provides gateway redundancy, and the default gateway redundancy is by using first hop redundancy protocol FHRP and its variations. Last layer for hierarchical network design is access layer. The objective with access layer is to grant user access to network applications and to network functions. For this, access layer incorporates switched LAN devices with ports that provide connectivity to different devices, to workstations, more importantly to IP phones, and also to access points. This is access layer, the place whereby devices that extend the network out one more layer are attached, and an example of that is IP phones or wireless access points. These technologies, they extend the network out one more level. Access layer provides local or remote workgroup access. Access layer also describes logical groupings of switches that interconnect end devices. In a WAN environment, this is in fact the access layer. that for teleworkers and remote sites may provide access to the corporate network across one technologies. Access layer supports high availability. So as you have noticed by now, availability is the common key that I use to describe functions of all these three layers: core, distribution, and access. So here with access layer again, we expect this layer to support high availability via default gateway redundancy similar to distribution layer. But unlike distribution layer, here with access layer, we expect it to use dual connections for redundancy from access switches to redundant distribution layer switches. So remember, dual connections from access layer switches to distribution layer switches. This mechanism that requires you to have dual connections from access switches to redundant distribution layer switches behind default gateway redundancy is referred to as First Sub Redundancy Protocol FHRP. Next, to realize convergence, access layer is expected to support inline power over Ethernet PoE for IP telephony, for thin clients, and for access points, wireless access points. And last but not least, access layer needs to provide services for additional security against unauthorized access by tools, and these security tools include port security, quality of service sometimes can help, DHCP snooping. DHCP stands for Dynamic Host Configuration Protocol, and DAI, Dynamic ARP Inspection, and finally the last security tool, IP Source Guard. Let's see DHCP snooping, DAI, and IP Source Guard in more details. Dynamic Host Configuration Protocol DHCP snooping provides security to the network by preventing DHCP spoofing. So we need snooping to prevent spoofing. And DHCP spoofing refers to an attacker's ability to respond to DHCP requests with false IP information. How does DHCP snooping do that? DHCP snooping acts like a firewall, sitting between untrusted hosts and or the DHCP servers. In this way, DHCP spoofing cannot occur. So when sitting in between, that means that DHCP snooping needs two types of ports or creates two types of ports. In DHCP snooping, we can have trusted ports and we can have untrusted ports. The network will only allow DHCP responses to DHCP requests from trusted ports, thanks to DHCP snooping being enabled on that network. And when we say the network only allows DHCP responses from trusted ports, those trusted ports usually are uplinks, as opposed to allowing DHCP responses from untrusted ports that can be attackers or responders with incorrect IP information. And attackers, they sit on untrusted ports, and those ports are usually edge ports. So edge switch ports are usually the untrusted ports. So uplinks towards DHCP servers are trusted ports, and untrusted ports are edge switch ports. DHCP snooping acts like a firewall and sits in between to only allow DHCP responses to DHCP requests from trusted ports. Next, dynamic ARP inspection. Remember, for having DAI in your network, you need also to enable DHCP snooping. Without DAI, dynamic ARP inspection, a malicious user can attack hosts, switches, or routers connected to a layer 2 network through poisoning ARP cache memory of systems connected to the subnet. And in this way, the attacker can intercept traffic intended for other hosts on the subnet. DAI, dynamic ARP inspection, prevents this type of attack. In fact, DAI intercepts, logs, and discards ARP packets with invalid IP to MAC address bindings. We know that ARP is intended to find the associated MAC address to an IP. With dynamic ARP inspection in place, this mechanism is going to intercept logs and discards ARP packets with invalid IP to MAC address bindings. Where do we get these bindings from? The address binding table is dynamically built from information gathered in the DHCP request and reply. And this can only happen when DHCP snooping is enabled. And that's why I said we need DHCP snooping to be enabled so that we can have DAI enabled. When DHCP snooping is enabled, then we can have address binding table being formed dynamically and built from information gathered in DHCP request and reply. So we store information in DHCP binding table, and as a result of that, the MAC address from the DHCP request is always paired with the IP address from the DHCP reply to create an entry in the DHCP binding table. This forms a valid IP to MAC address binding. Now, if any attacker wants to respond to ARP request of a victim by providing a malicious MAC for the ARP request, with this information inside the HCP binding table, we can stop him because we know the exact and the valid IP to MAC address bindings. At very beginning of this scenario, when a machine comes up and wants to get IP address information from the HCP server, the address binding table is dynamically built from information gathered in DHCP request and DHCP reply once DHCP snooping is enabled. And that means we know exactly which MAC address from the DHCP request is paired with what IP address from the DHCP reply. And this binding creates an entry in the DHCP binding table. And that helps us later to do dynamic ARP inspection, DAI, when a malicious attacker wants to poison the cache, the ARP cache, and for that it uses the Rouge ARP requests and replies. We next see IP source guard. This tool provides security to network by filtering clients with invalid or spoofed IP address What does that mean? First, remember IP source card is a layer 2 port-to-port security feature that works very closely with information that we have in DHCP snooping binding table. So again, similar to ARP inspection, dynamic ARP inspection, here with IP source guard, again we are relying on DHCP snooping binding table information. When you enable IP source guard on an untrusted port with DHCP snooping enabled, an IP filter entry is also created or deleted for that specific port automatically. And this is based on information stored in the corresponding DHCP binding table entry. For instance, when a connecting client receives a valid IP address from the DHCP server, a filter is installed on that port in order to allow traffic only from the assigned IP address from the DHCP server. That simply prevents traffic from any other host, and therefore it prevents traffic attacks if a given host tries to use the IP address of its neighbor. So this is very important. And if, let's say, the threshold is 10, a maximum of 10 IP addresses are allowed on each IP source guard enabled port. So for each port for which IP source guard has been enabled, a maximum of 10 IP addresses are allowed. As soon as this number is reached, no more filters are added. So no more filters are set up and the traffic is going to be dropped. This is important to remember, that while dynamic ARP inspection blocks only ARP packets, address resolution protocol, IP source guard blocks all IP packets. And again, IP source guard is successful thanks to the DHCP binding table. So DHCP snooping, we have seen that acts like a firewall between untrusted hosts and DHCP servers. You use DHCP snooping in order to differentiate between untrusted interfaces connected to end users, let's say, and trusted interfaces that are connected to DHCP server or another switch. For DHCP snooping to function, it is important to remember all DHCP servers must be connected to the switch through trusted interfaces. When a switch receives a packet on an untrusted interface and the interface belongs to a VLAN in which DHCP snooping is enabled, the switch then compares the source MAC address and the DHCP client hardware address. Afterwards, that switch forwards the packet received from a client on the untrusted port only and only if the source MAC address and the DHCP client hardware address match. So if the address match, those two addresses match, then the switch is going to forward the packet. If the source MAC address and the DHCP client hardware address, these two addresses, they do not match, then the switch is going to drop the packet. So an untrusted DHCP message is a message that is received from outside the network or firewall somewhere, not on the trusted ports. Same sort of binding is used in ARP inspection, and same is used in IP source guard, a security feature that restricts IP traffic on non-routed layer 2 interfaces. As I mentioned earlier, it's a layer 2 uh, security tool by filtering traffic based on the DHCP snooping binding database. Uh, though it can be manually configured as well for the bindings. The aim of IP source guard is to prevent traffic attacks if a host tries to use the IP address of its neighbor. You can enable IP source guard, as I said, when DHCP snooping is enabled on an untrusted interface. And as soon as IP source guard is enabled on an interface, the switch blocks all IP traffic received on that specific interface except for DHCP packets allowed by DHCP snooping. How this is realized? Well, a port access control list is defined and applied to that interface. Port access control list allows only IP traffic with a source IP address in the IP source binding table, and that access is going to deny any other traffic. All other traffic will be denied. So bear in mind that IP source guard, in order to only allow IP traffic from a specific source IP, and in order to deny all other traffic, it uses a port access control list. Port access control list takes precedence over any router access control list or VLAN maps that affect the same interface. This is also important to remember. And finally, to wrap up, all these things are feasible and doable thanks to a binding table. So IP source binding table here, in this case with IP source guard, has bindings that are learned by DHCP snooping. So this DHCP snooping is the cornerstone for all these technologies. Of course, for IP source guard, we can add entries manually. That is static IP source binding. And entry is created in binding table with information such as IP address, its associated MAC address, its associated VLAN number, these three, remember. The search uses the IP source binding table utilized whenever IP source guard is enabled. IP source guard is supported only on layer 2 ports once more, and it can include access and trunk ports. You can configure IP source guard with source IP address filtering only, or with a combination of source IP and MAC address filtering as well. Here we have campus network architecture. We would like to talk about VLANs and trunking based on the standard IEEE 802.1q. Trunking protocol is defined as a special protocol which is used in order to carry multiple VLANs over a single link between two switches, between two devices. There are two trunking technologies, ISL and IEEE 802.1q. ISL, it stands for Interswitch Link ISL, a Cisco proprietary trunking encapsulation. The second trunking encapsulation protocol is IEEE 802.1q and is known as an industry standard trunking method. Comparison between ISO and 802.1q is important. Remember, the one that we stick to is .1q because it has smaller frame overhead than ISO, and when we have smaller frame overhead, that means that the protocol is more efficient. With .1q, we want to have 4 bytes more for the header, while with ISL we are having 30 bytes of overhead, and that's why we stick to .1q over ISL. Another reason for choosing .1q is the fact that ISL is Cisco proprietary, whereas .1q is the standard. That's why we always go with this standard. And finally, we choose .1q over ISL because it has support for IEEE 802.1p fields, which are used for quality of service. The figure here is very important. At first, what you see is the standard Ethernet frame. So it has destination 6 bytes, source 6 bytes, length of either type for 2 bytes, and then we have data, and finally frame check sequence FCS 4 byte at the end. Thanks to 4 bytes that we insert into the Ethernet frame called tag for 4 bytes after destination and source MAC addresses, we are able to distinguish different VLANs from each other, and in this way a single link between two devices can carry traffic for multiple VLANs because we know each frame belongs to which VLAN thanks to tag. Tag fields are also shown here, either type, priority, CFI, and VLAN ID. IEEE 802.1q tag, or that 4 bytes tag that I've just mentioned, has two main parts, each part 2 bytes. We have VLAN protocol ID, VP ID, or either type, which is 2 bytes, and then the second half is TCI tag control information. So TCI tag control information consists of priority, CFI, and VLAN ID, 3 bits, 1 bit, and 12 bits respectively. Tag protocol identifier, here in this case either type, for hexadecimal value 8100 in 2 bytes, is here in order to tell us in 16-bit field that the frame is an IEEE 802.1q tagged frame. So tag protocol identifier TPID identifies the frame as, in this case, IEEE 802.1q tagged frame based on the value 8100 in hexadecimal. Then the last 2 bytes are TCI tag control information. As I just mentioned, we're going to have the first 3 bits of the TCI as PRI priority for 802.1p layer 2 COS class of service. Shortly, I'm going to discuss the difference between what we have as TOS versus COS. For now, just bear in mind that 802.1p defines the first 3 bits of the tag control information TCI in order to define user priority. given 8 priority levels because 3 bits means 2 to the power of 3 equals to 8. IEEE 802.1p defines the operation for these 3 bits called user priority. Then inside the .1q tag we have CFI, canonical format indicator, is a single bit flag and is always set to 0 for Ethernet switches. In fact, CFI is used for compatibility between Ethernet and token ring networks. So if a frame received at an Ethernet port and has a CFI set to 1, then we are simply telling the switch that that frame should not be forwarded as it is to an untagged port. But here with Ethernet we set CFI to 0. Last but not least, VLAN ID 12 bits is the main focus. VLAN identifier. The VLAN identifier 12-bit field uniquely identifies the VLAN to which the frame belongs. And thanks to this field, trunk ports can carry traffic for many VLANs. Bear in mind that the minimum size of the Ethernet frame without tag was 64 bytes. Now with 4 bytes tag, the minimum size of the Ethernet frame with 802.1q tagging is 68 bytes. This is because we have 802.1q tag of 4 bytes size, and the resulting Ethernet frame can be as large as 1520 bytes, because the maximum for normal Ethernet frame is 1518, and with 4 bytes tag we can have as large as 1522 bytes Ethernet 802.1q tagged frames. Just a bit more on quality of service. Quality of service is a general term. We use this term in order to talk about classifying or prioritizing traffic in the network. For instance, we would like to prioritize voice over IP traffic over FTP traffic. Quality of service is your concept of preferring things over each other and making policies accordingly. Why do we need to classify network traffic at all? Classifying network traffic allows you to see the kinds of traffic you have in your network and therefore treat some types of traffic differently than others. So, for instance, identifying and organizing network traffic allows you to allocate network resources in order to deliver the best performance for each type of traffic. QoS, quality of service, is how to manage your traffic. Quality of service is essentially classification, meaning that which type of traffic we're talking about. Quality of service is congestion management or provides congestion management, meaning that how to manage a congestion. Quality of service also covers congestion avoidance, meaning that we want to see how to prevent the congestion. Quality of service has to do with policing. For instance, we can say after a threshold, a certain threshold, for instance, we can say we can drop traffic. Course or quality of service is also about shaping traffic, meaning that we say, okay, we don't drop, but we use buffers as possible. And also quality of service has to do with signaling, meaning that we want to reserve bandwidth for traffic, and therefore we can have link efficiency thanks to quality of service. We can have fragmentation and interleaving, placing traffic type A after type B, and so on and so forth. So you can see that the domain of discussion for cost or quality of service is quite broad, with areas or sub areas like classification, congestion management, congestion avoidance, policing, shaping, signaling, or link efficiency. Here, I'm going to talk about two ways to deploy quality of service in a network. We have TOS, TOS, type of service, and we have COS, COS, class of service. So type of service and class of service as two ways in order to deploy quality of service in the network. When I'm talking about TOS, TOS, bear in mind that I'm talking about layer 3 or network layer. So TOS fields are in fact fields at IP layer protocol. Fields such as DSCP inside IP header. DSCP stands for Differentiated Services Code Point. So DS differentiated services. So type of service or TOS has use cases like, for instance, DSCP46 can be used for VoIP RTP, or DSCP26 is used for SIP, Session Initiation Protocol, for VoIP signaling. So you can see that you can mark packets based on DSCP field, and packets, when they arrive into a router, we can put them into queues and apply quality of service, like prioritize some traffic like VoIP sensitive traffic over data or bulk or video traffics. So thanks to tools in layer 3, we mark packets, we queue them, we prioritize some kind of traffic over other kind of traffic. However, COS, COS, or class of service, is a layer 2 concept. 802.1q and 802.1p are layer 2 concepts, and .p protocol is a subset of .q protocol. So it is used by .q VLANs in order to prioritize traffic according to the kind of VLANs. So switches, when they want to select which VLAN traffic should be prioritized, then they use 802.1p field, priority or user priority, that I just spoke of. Let's say you have a dedicated voice VLAN as best practice. Let's say VLAN 100 is for VoIP telephones, and then if you're using VLAN 100, that means that you can set 802.1p into category number 4 for voice for this VLAN 100, and that means the switches along the path they're going to select VoIP traffic and treat them with priority, because the 802.1p field is set to category number 4 for voice, and voice is a delay sensitive traffic. So in a nutshell, that was tools versus calls, type of service versus class of service, one in layer 3, another in layer 2. So the first takeaway point for you is that don't confuse type of service tools and class of service calls. Tools is found under the header of IP packet, so in layer 3. Whereas calls class of service is found in the header of 802.1q, so it's in layer 2 and it's used for quality of service on trunk links. In fact, type of service TOS is a byte in IPv4 header which is used for precedence, or in other words, in order to categorize traffic classes. So we can have precedence 0, we can have precedence 1, precedence 2, precedence 5, and then we can say precedence 0 is the routing or normal traffic, whereas precedence 5 is critical traffic, for instance. In the modern network, as the later RFCs suggest, TOS or type of service is used for differentiated services, DS, and in particular DSCP. So TOS field, that one octet or that one byte that we are talking about inside IPv4 header in modern form is DSCP. But in earlier RFCs, they say that TOS bytes, that octet can be IP precedence. So earlier IP precedence, nowadays it is DSCP. If IP precedence is concerned, then the first 3 bit of this byte indicates the precedence. If it's later version DSCP, then the first 6 bit of this byte indicates the DSCP value. No matter which, remember TOS is a layer 3 concept. IP precedence and DSCP each use TOS field, this 1 byte field, in the IP header, but they can be interpreted differently and with different bit size. They are both considered as tools available to implement quality of service. So every IP packet, IPv4, IPv6, it includes a TOS byte, though in IPv6 we call it traffic class byte. This field and the bits inside this byte, this 1 byte, is to provide the appropriate quality of service commitments. Earlier RFCs suggest that the first 3 bits contain the IP precedence value. Later RFCs, they say that in case of differentiated service, first 6 bits are called DSCP in IPv4 TOS octet or IPv6 traffic class octet. The theory behind both IP precedence and DSCP are the same. You can place network traffic with a specific IP precedence into one traffic class while you place traffic with another, let's say differentiated services could point DSCP value into another traffic class. Each traffic class later can be given a different quality of service treatment. And for that, you need to configure a policy map. So you define each class of traffic in what we know as class map, and later you define policy map to specify how you want to treat them. And different class maps are defined based on criteria such as IP precedence or DSCP. Also, to note that normal application traffic is not permitted to use IP precedence high values like 6 or 7. And this is because they are strictly reserved for network purposes like keep alive packets, for instance, or routing protocols. communication, because no matter what, the network must always give these sort of packets higher priority over any other application packets, because no application will work if the network loses its topology information. So we need to give more priority to topology information packets. If you see the relevant RFCs, you may get confused. Remember, sometimes they speak of type of service TOS byte, and they are referring to this one octet. Whereas sometimes they're talking about type of service TOS bits, like the one that we had here, like 3 bits of this byte is used for IP precedence, the first 3 bit, or in later versions DSCP, the first 6 bit of TOS byte. So if they are speaking of type of service bits, be careful, don't confuse that with type of service byte. At the end of the day, it's one octet, one byte consisting of 8 bits. Old RFCs, they suggest that the first 3 bits are used to define a precedence, and the higher the value, the more important the IP packet is. Newer RFC, we have seen they use a concept called differentiated services DS. That's why TOS byte is given sometimes a new name when we are calling uh, new RFCs. TOS byte inside IPv4 IPv6 header, and that name is DS field, so differentiated service DS. So DS field is the same as TOS byte or TOS field as with newer RFCs. And there, the first 6 bit defines DSCP. Second category, COS, COS, or class of service. This is a field in Ethernet header. So TOS was in IP header, COS is in Ethernet header. And to be more precise, it's inside IEEE 802.1q tag that we see COS value, equivalent to user priority or priority, as you can see in this figure. So priority is a layer 2 class of service, COS tag inside.1p inside.1q, and it can be used for categorizing traffic. With 3 bits we're going to have 8 different values, 0 to 7, and this is going to work at layer 2. COS is 802.1p within 802.1q header, 3 bits at layer 2. It acts as another place for us to mark frames in order to implement quality of service policy. So with IP precedence as well as DSCP, we mark packets in order to implement a QoS quality of service policy. Here we mark frames thanks to QoS or 802.1p within 802.1q header in order to implement a QoS policy. Also keep in mind that when we are saying it's a layer 2 concept, that means that your IP header remains intact end to end, because we are talking about a field inside .1q tag defined by .1p standard on the Ethernet. That means Ethernet header, and that means a hop by hop paradigm within an layer 2 network, which is going to be changed before moving on to the next hop. So you're going to have COS tags Class of service tags on 802.1p links as an extension of IEEE 802.1q VLAN tagging on trunks. You can classify traffic based on this field, based on this 3-bit field as defined by IEEE 802.1p, and you do that in order to support quality of service calls. The value for calls is encoded in the high order 3 bits of TCI tag control information inside that one queue header, and therefore it is called user priority or calls tag. Class of service can be thought of as a queuing discipline, as an algorithm that compares fields of different frames based on their calls tags and assigns frames to different queues with different priorities. So it can be also similar to the IP precedence and DSCP as far as classification is concerned. However, unlike TOS field, COS field is a layer 2 concept. It is only 3 bits, so 8 different levels or values starting from 0 to 7. And an example of that is, for instance, Cisco IP phones. They can tag voice traffic with COS value 5. Then you tell the switch that is connected to IP phones that you want to apply quality of service in order to separate your voice traffic. Then you use COS value 5 in this example. Here, I would like to talk about multi-layer switching or multi-layer switches, MLS, and we would like to see a few minutes nuts and bolts about multi-layer switching. Switches, they operate at layer 2, and routers, they operate at layer 3, so we never saw them meeting each other. With MLS, we're going to see this happening. Layer 2 and layer 3, they're going to meet up in a device called multi-layer switches or layer 3 switches. So MLS or layer 3 switches are devices that not only can switch but also can route packets in the switch hardware itself. With this definition, remember, I'm talking about packets. That implies layer 3 encapsulation. And then also I'm talking about switch hardware itself. So I'm talking about hardware rather than software. So multi-layer switching or MLS, devices that switch and route packets in the switch hardware itself. Benefit is to get layer 3 involved on the same device. So we don't need to have both routers and switches to get layer 3 involved. Now with MLS on the same device, we can have both layers involved. So we can have also layer 3 involved. And this is thanks to this switch hardware that is different with MLS or more advanced with MLS. Probably the MLS concept to have layer 3 involved on the same switch device goes back to the time when wireless came out. Uh, the good thing about MLS is that it enables us to have inter-VLAN communication without having to bringing in a separate router. So we have traditionally router on a stick, ROAS topology, whereby a router is there, and thanks to this router, two hosts in separate VLANs are able to communicate with each other. So to get involved, layer 3, here we need a separate router. But thanks to MLS, we don't need routers anymore. So if two hosts in separate VLANs are connected to the same switch, layer 3 switch or MLS, the correct configuration allows that communication without data ever leaving the switch or the MLS. Whereas traditionally we had a router, data had to leave to a layer 3 router. With MLS scenario, communication happens without data ever leaving the MLS. I keep repeating the notion of hardware switching or hardware based packet processing because this is really important and this is a foundation for multi-layer switching. So with catalyst switches, hardware switching is performed by what we know as a router processor or it is called layer 3 engine. So whatever term you want to call it, a router processor is in fact involved in that MLS that allows us to do hardware switching. This layer 3 engine or router processor must download routing information to hardware itself. See, I keep repeating to hardware or hardware switching. This is to make this hardware based packet processing happen. And for this, switch will run either the legacy MLS or newer CEF Cisco Express Forwarding. What really makes the difference between the legacy MLS scenarios or the CEF Cisco Express Forwarding the newer version scenarios for MLS multi-layer switching is in fact the MLS switching method itself. So two MLS switching methods we have here, we have root caching and also we have CEF. So root caching is what you see with legacy MLS scenarios and CEF is what we see as the state of the art. I go through legacy first and then we explore CEF. Before I go to the comparison between legacy MLS scenarios with root caching against the state of the art CEF, Cisco Express Forwarding, let's see the role for ASIC or application specific integrated circuits, ASICs. Well, as packets, they go across the network. We know that the source IP and destination IP of a packet they do not change as the packet goes across the network. However, MAC will change. With multi-layer switching, it is in fact ASICs or application specific integrated circuits that perform layer 2 address rewriting for us and they rewrite layer 2 addresses. So they actually perform that layer 2 overwriting for us. Next, we have CAM and TCAM tables. We want to see what they are. We have content addressable memory or CAM tables, and we have ternary content addressable memory or TCAM tables. CAM tables, we already saw that with ordinary layer 2 switches. CAM tables are also known as bridging tables. They are also known as MAC address tables or switching tables. These terms can be interchangeably used to describe what we know as CAM tables. So the concept of CAM tables, it is still present in multi-layer switching. But in addition to that, we have TCAM or ternary content addressable memory. This is because a simple CAM table cannot handle all routing, all quality of service, or access control list information. So we need to have another table called TCAM with MLS or multi-layer switching. So in addition to CAM tables with multi-layer switching MLS, we have TCAM. And TCAM basically stores everything that CAM table cannot. And this everything includes information regarding quality of service and access control lists. So with legacy MLS scenarios, we have the notion of CAM and also TCAM to store information that ordinary or normal CAM table cannot, and that information includes quality of service and access control list information. This is in addition to normal switching table, CAM table that we have here with MLS as well as with ordinary layer 2 switches. Now we want to see the heart of legacy MLS scenarios, that is the specific switching method for it called route caching. And then we want to compare that with the CEF scenarios. With route caching, or the first MLS switching method or multi-layer switching method that we have here, devices have both routing processor as well as switching engine. So we still need both engines. We need routing processor as well as switching engine. Routing processor routes a flow's first packet. So it's there for routing the first packet of a flow. Then switching engine takes over, snoops in on that one packet, on that one very first packet, and the destination of it, and then the switching engine is going to forward the rest of the packets in that specific flow onwards. So once again, the routing processor with legacy MLS scenarios, what it does is that it routes a flow's first packet, then switching engine snoops in on that packet and destination of it, and then the switching engine takes over and forwards the rest of the packets in that flow onwards. When I say a flow, it is unidirectional stream of packets. You know that. From a given source to a given destination. So simply from point A to point B. And such packets get sent by a given protocol. It can be www, it can be TFTP. So these specific packets from A to B are sent by a given protocol, and they will be part of a single flow. That is, if a source is sending www or TFTP packets to the same destination from A to B, we're going to have two different flows of traffic because we have two different protocols there. And with this first MLS switching method, that is route caching, you see how MLS cache entries can support such unidirectional flows. The way that they do it is to route a very first packet of a flow through the routing processor, and then relying on switching engine to switch the rest of the packets in that flow. Route caching can be effective, but there is one shortcoming there. The very first packet in any flow will be switched by software, because as I said before, the routing processor, when we say that, we mean some software there sitting and calculating the best path for that very first packet of a flow. Even though all other packets in that specific flow, let's say, will be hardware switch, and when I say hardware switch, this is thanks to the switching engine that took over after the very first packet of the flow was routed. It is more effective to have all of the packets, including the very first packet of a flow, to be switched by hardware rather than software. And this is exactly where CEF, Cisco Express Forwarding, comes in to play its own role. So, to sum up, before I move on to CEF, with route caching as the first MLS switching method that we have investigated, the very first packet in any flow will be switched by software through router processor.
As we also have switching engine, even though all other packets in the flow will be hardware switched through this switching engine, it is more effective to have all, including the very first packet, all packets to be switched by hardware rather than software. The switching by hardware is deemed to be more effective than switching by software or routing. And now we move on to our second MLS switching method, that is Cisco Express forwarding, a very highly popular method for MLS switching that is primarily designed for backbone switches, a topology based switching method. And Ceph, this topology based switching method requires special hardware. No surprise, you have seen that with these advanced switching methods, we always need special hardware. So in the past, probably Ceph was not available on all layer 3 switches. With modern switches, it's not the case anymore. We have them. Ceph is highly scalable and is easier on a switch's CPU than root caching, the previous method that we have seen. Ceph has two major components. We have FIB, forwarding information base, and we have AT, or adjacency table. These two are two major components of Ceph. Let's see FIB and then AT. CIF enabled devices, CEF enabled devices, they have the same routing information as a router. But unlike routers, this routing information is not found in the typical routing table. Instead, we have forwarding information base or FIB, and FIB contains usual routing information that we need, like the remote networks, like masks, next hop IPs, etc. And Ceph uses FIB to make layer 3 prefix based decision, similar to a router with routing data. So Ceph uses FIB to make layer 3 prefix based decisions. FIB's contents will mirror that of the IP routing table in routers. This is because FIB is really just IP routing table, but in another format. So concept-wise, FIB is the same as IP routing table. In reality, FIB is really just IP routing table in another format. The second major component of Ceph is AT. We have seen how FIB takes care of layer 3. Now with adjacency table or AT, we take care of layer 2. And this is where the AT comes in with layer 2 decisions. So a host is considered adjacent to another host if they are just one hop apart or away. As adjacent hosts are discovered via ARP address resolution protocol, that next hop layer 2 information is kept in the AT or adjacency table. And this is used for Ceph switching method. Should either TCAM or AT hit capacity, there is a wildcard entry that redirects traffic to the routing engine. But hopefully that won't happen. But if it happens, we still get things done, just not as quickly as we might like, but still doable. So with FIB and AT, Ceph works very well. FIB contains layer 3 information and is created by IP routing table in another format. And AT or adjacency table contains all layer 2 information that we need and is created via ARP or address resolution protocol table. At this point, MLS is just about ready to forward the packet with Ceph switching method. The MLS switch will make the same changes to the packet that the router would. And this means that we're going to change the layer 2 MAC address to next hop MAC address, and layer 2 source address will also change as well to MAC address on the switch interface that is actually transmitting that packet. And source IP and destination IP, they will not change as a packet goes across network. So again, our layer 3 addresses, they do not change. Our layer 2 addresses, they do change. And this is how it happens. Enabling Cisco Express forwarding is very easy. This is because Ceph is on by default on all Ceph enabled switches. So remember that you cannot turn it off. We don't have no Ceph command at the CLI. We don't have such a command. Ceph is on by default because Ceph is hardware based rather than software based switching method. However, a multi-layer switch must have IP routing enabled in order for Ceph to run. So you need to enable IP routing on a multi-layer switch so that you can have Ceph running there. Recall that with ordinary layer 2 switches, we had management interface, and by default, it was interface VLAN 1. Interface VLAN 1 on an ordinary switch, layer 2 switch, is actually what we know as SVI or switched virtual interface. With an ordinary layer 2 switch, the only default SVI was VLAN 1 or interface VLAN 1. With MLS here, we can create an SVI for any VLAN. And creating an SVI for any VLAN is very similar to creating a loopback interface. So on the configuration mode, you create that SVI, you give IP, and then that's it, you're done. And that SVI represents a VLAN. MLS therefore allows you to create a logical interface or SVI or switched virtual interface representing a VLAN. In addition to that, on MLS or layer 3 switches, we also have the option of configuring a physical port on that MLS switch as a routed port. And that is used when that port is connected to a router. So we are talking about a routed port on an MLS being connected to a layer 3 router. You assign an IP address to that routed port on the MLS the same way that you would do with an SVI, but there is an additional configuration step here. Routed ports are physical interfaces, unlike SVIs. So routed ports are physical, SVIs are logical, and therefore routed ports, unlike SVIs, they do not represent a particular VLAN, as does an SVI. Imagine that we have a router, and that router is connected to an MLS through a routed port. Even though the IP routing is enabled, the ports on our MLS on that switch are still in layer 2 mode because that's the default for Cisco MLS switches or layer 3 switches. Therefore, to configure a routed port on that MLS on the switch port connected to that router, we use no switch port command followed by the desired IP address. And when you configure, at first you see the line protocol is on, the switch port goes down, but comes back very quickly in a few seconds, and that's very normal and expected behavior. Later, you can verify addressing and status for the routed port on the MLS, which show interface command. You can see whether IP line protocol is up, and also you can verify layer 3 status of that routed port with show interface switch port to make sure that layer 2 switch port is disabled for the routed port. So to summarize what we have discussed here, we used to have VLAN 1 with normal layer 2 switches as the only default switched virtual interface or SVI to be used for management purpose as a management VLAN. On MLS, SVI allows you to create a logical interface to represent a VLAN. And on MLS, we also have the option of configuring a physical port as a routed port. And routed port is a physical port, unlike SVI, that is a virtual or logical interface. Routed port, if it is connected, let's say, to a layer 3 router or layer 3 device, then you can assign IP address in a similar way that you assign IP address to SVI. So you assign an IP to a routed port the same way you would to an SVI. However, routed ports are physical interfaces, as I said, and SVIs are logical interfaces. Cisco Express Forwarding, we know that it is on by default on MLS if it is supported. However, you need to enable IP routing for Ceph to run on MLS. Layer 2 switch port needs to be disabled explicitly for a routed port on MLS that is connected to a router, layer 3 router. And this can be verified as I discussed with show interface switch port command. This short introduction on MLS brings us to the next topic, that is logical switching architecture. Let's first see why we need virtualization at all. Well, we know that for the sake of redundancy, we need to link access switches to distribution switches. So access switches, they need their own uplinks to each of the distribution switches in order to satisfy the redundancy requirements. But at the end of the day, one of the uplinks has to be blocked by the STP or spanning tree protocol in order to prevent a loop, consequently cutting the bandwidth in half. So as you can see from the figure on the top right hand side of this slide, we cut the bandwidth in half when we use STP and we block one of the uplinks from access to distribution layer. To overcome some of these limitations, Cisco proposes virtualization solutions. And two virtualization solutions in particular we have here. Firstly, we see Stackwise, and then we go to VSS. For now, remember Stackwise, it is around the access layer module, and VSS is focusing on the aggregation layer module. So Stackwise for access layer and VSS for aggregation layer. Let's start with Stackwise, and remember we are focusing on access layer. Stackwise or Cisco Stackwise technology, it provides a method for collectively utilizing the capabilities of a stack of switches. And as I said, we are focusing on access layer here. This means that up to 9 separate switches can be merged together and can be joined, and then the configuration and routing information is shared between all these up to 9 switches that we have in the stack. So up to 9 switches can join, creating a single switching unit. And this is Stackwise. Switches can be added to or deleted from a working stack without affecting the performance. And this is great. The whole stack is managed as a single unit by a master switch. And as we have a few switches here, we need one switch to be the bus, and the bus here is the master switch. We shortly see how the master switch selection is done. We need to have an election for it. But for now, remember, master switch is elected from one of the stack member switches. And also, this stack-wise technology it allows for any member to become the master in case the previous master ever fails. Switches are united into a single logical unit in Stackwise. And this is doable thanks to special stack interconnect cables. And these special cables, what they do, they create a bidirectional path over which network topology and routing information can traverse. So network topology and routing information is updated continuously through the stack interconnection. And all stack members have full access to the stack interconnect bandwidth thanks to Stackwise technology. So each stack is corresponding to a single object, and each single object or each stack is corresponding to single IP. Each switch in the stack shares same MAC address and routing information, and we will see that later as well. So for now, remember, we can have different models of switches. We can have Catalyst 3750 E or X series, or we can have 3850 series switches. They support not only Stackwise but also Stackwise Plus. Stackwise Plus is another variation of Stackwise, with Stackwise Plus as an evolution of Stackwise. We can support local switching as well. Locally distinct packets, they do not need to traverse the stack ring in order to get to destination. With Catalyst 3850, with these series, we also have something called Stackwise 480. And if switch supports this one, then we have improved 480 gigabit per second stacking. With Catalyst 2960S series, we can support Flex Stack. Flex Stack is a Stackwise based feature tailored for layer 2 switches. And with Flex Stack, we're going to have up to 4 stacked switches. We will see later we have Cisco Catalyst 4500 and 6500 series. They also support something similar to Stackwise called VSS, but we see that later. They are all different variations for the same concept. That is Stackwise. So we have multiple switches, and multiple switches are used in order to provide enough access ports to our corporate network users. The stack, i.e., up to 9 switches, is managed by a single unit, and this, of course, reduces the number of units that you have to manage as a network administrator in your network. Switches can be added to or removed from a working stack without any affection on stack performance. And this is the good news, and this is what we are after. When a new switch is added, all happens is that the master switch automatically configures the unit, the newly added unit, with the currently running iOS image of the stack. And the configuration of the stack will be dispatched to this newcomer. You don't need to do anything else. So you do not have to do anything to bring up the newcomer or the newly added switch before it is ready to operate, because master switch takes care of everything for you. You can see how we can verify stack-wise configuration using show switch command without any additional parameters. We see it returns the shared stack MAC address because, as I said, each switch under this stack shares the same MAC address and routing information, and lists all switches in the stack with their stack number towards the bottom left hand side of the slide, stack role, MAC address, hardware priority, and hardware version. Both can be verified, and also the current state is verifiable thanks to show switch command. Remember, hardware priority is used in stack master election. So the way that we choose master switch under the stack, it depends on the hardware priority, and we will see that later. And this priority is configurable, so it can be configured. We have hardware version, and that has to do with the model. So hardware version number is associated with the switch model itself. Different switch models, of course, can have the same version, the same hardware version, if they support the same system level features. But hardware version number is not used in the stack master election. And this is mainly because, as we see here, even different models, they can have same version in case they support the same system level features. So we need a distinct characteristic that is hardware priority to elect our master switch in our stack. We also have show switch stack ports verification command. Well, if you look at the rear of a Cisco Catalyst, let's say 3750 series switch, what you see is the stacking connectors. You can see two connectors on the left side, and let's name them stack 1 and stack 2. You also see the stack-wise cable if you have used one of them for stack-wise configuration. And we know that StackWise is Cisco's access layer technology for allowing multiple switches to be united together and to be managed as a single unit. Now you see how using the stacking connectors, this is doable. So access layer switches used to be all separate physical switches where we use Ethernet cables for connectivity between them. But with StackWise, we have changed this paradigm, and it allows us to turn multiple physical switches into a single logical switch. Switches that support StackWise, they use a special stacking cable to connect the switches to each other, and each switch has two stacking connectors that are used to daisy chain or to loop the switches under the stack together. Each switch is connected to the one below it, and also the bottom switch will be connected to the one on the top. Next, I would like to talk in more details about StackWise. We have seen StackWise how it gives you the ability to physically link up to 9 switches. And remember, we are focusing on access layer with StackWise technology. So 9 switches of access layer in order to create a hole. And that hole is a switch unit, or what we know as switch stack. So StackWise, we need special stack interconnect cables to do that. So physically, linking up to 9 switches to form a single stack or single switch unit is the focus here. When we do that, what we end up with is a fully functioning bidirectional path, and each path supports up to 16 gigabit per second. So in each direction, 16 gigabit per second means we are looking at 32 gigabit per second overall of capacity when we are using stack interconnect cables. And with this special cable, we are physically linking up to 9 switches with stackwise technology. So the fully functioning bidirectional path is in fact two-way path. So 16 gigabit per second each direction, together 32 gigabit per second overall capacity. As there are a number of switches, as you may guess, we need one to be the boss. So when we have number of switches, one switch needs to be the boss. And for this reason, with stackwise technology, boss is called master. So master switch amongst multiple switches that we have is the boss, and the name master is aptly named. The master switch has quite a workload to do. So master switch workload starts with downloading forwarding tables to non-masters. Secondly, master switch sends access control list and quality of service information to non-masters. Thirdly, when a new switch is added or when an old switch is removed, it's in fact the master switch that lets others in stack know about it. Fourthly, master switch keeps what we know as master MAC address table and sends that table to all non-masters. So it's master switch who is responsible for maintenance of MAC address table and also updating other non-members about it. Fifthly, master switch is the one that handles all pings and all telnets to that stack. So when you ping or when you telnet to stack, it's master who is responding. And master handles the connection for pings, for instance, in this case. So that's why master switch election is important. We carry out election to specify uh, the master switch, and this is because we are Democrats. We want to see at very beginning what the administrator thinks about the result of the election. So administrators have the ability to choose a particular switch to become the stackwise master. So at very beginning, the first priority or the first point to check for determining the master switch is to see if admins they select a particular switch to become master. But if admins they don't care, and as we have 9 switches of the exact same capacity, let's say, the switch with the best feature set is going to be master switch. And when I say the best feature set, I mean the most extensive feature set. The feature set with the most features, if you wish, is going to become the master switch. If there is still a tie there, then a switch that has been pre-configured wins over switches that have not been pre-configured. Because at least with pre-configured one, we have some configuration there. So pre-configured over those that have no configuration at all are preferred. So that one becomes the master switch of Stackwise. If that's still a tie, the switch that's been up the longest wins the election. And this is the fourth criterion to be checked: longest uptime. And finally and fifthly, if those are all ties, then we need to go with a tie breaking criterion at the end of the day. You know that MAC addresses has to get involved in any selection process towards the end to ensure the tie breaking factor there. So the search with the lowest MAC address wins the election and becomes the stack-wise master. If I am focusing on access layer of our architecture, then I'm talking, let's say, about Cisco Catalyst 3750 series. But if I am focusing on aggregation layer, then I'm talking about Catalyst 4500 or 6500 series. And then we have two different virtualization solutions here. With 45, they support something similar to Stackwise, and that is called VSS. And we're going to see that in the next slide. But for the moment, I'm focusing on access layer, Catalyst 3750 series, for instance. I talked about stacking connectors. Uh, if you see the rear of a Cisco Catalyst 3750 switch, you can see two connectors on the left hand side. They're labeled stack 1 and stack 2. I've gone through this before. What the stackwise cable looks like, you can see that if you search. Cisco's access layer switches used to be all separate physical switches where we used to use Ethernet cables in order to provide connectivity between these switches. But with the advent of Stackwise, uh, this has changed. So Cisco Stackwise changed this and has brought up new paradigm. It allows us now to turn multiple physical switches into a single logical switch or stack. Switches that support Stackwise use a special stacking cable once again to connect the switches to each other. Each switch, when it has two stacking connectors, that these two can be used to daisy chain or to loop all the switches together within the stack. Each switch is connected to the one below it, and the bottom switch will be connected to the one on the top. This way. The stackwise cable is like an extension of the switching fabric of the switches. This means when an Ethernet frame wants to be moved from one physical switch to another switch inside the same stack or switching unit, the stackwise loop is used. So, as I said, up to 9 switches are daisy chained or looped, and that loop is used for that Ethernet frame to be moved from one physical switch to another. What is good about this design is that using a cabled loop, you can remove one switch from the stack and the loop will be broken, but the stack itself will keep working. So when we have a loop here, you can remove one switch from the stack because the stack will keep working. So no disruption happens there. So one switch in the stack becomes the master, and master switch does all the management tasks for us for the entire stack. All other switches in that stack are members. If the master switch fails, however, another member will become the new master. To select a master, Stackwise uses an election process once again. And for the election process, Stackwise checks for the following criteria in order of importance. Firstly, the admin priority, because we can configure priority to decide which switch becomes the master. The second criterion is the hardware or software priority. As I said, the switch with the most extensive feature set has a higher priority than another switch. And when I'm talking about hardware software priority and also the extensive feature set, we can think of IP services versus IP based packages with Cisco, and I will go to that in more details later. Thirdly, the third criterion is the configuration, because a switch that already has a configuration will take precedence over switches with no configuration at all. Fourthly, uptime, the switch with the longest uptime will become the master. And fifth and finally, the switch with the lowest MAC address will win the election. So bear in mind that it makes sense to choose the master ourselves as admins. So normally we use the user priority to configure the master. Once the stack has been created, the configuration of the switches is the same as if it were all one single switch. Remember that all members of the stack they share the same management IP address and host name as the master. So all switches within the stack, same management IP address, same host name. The entire stack has one IP address and one configuration file. And that configuration file is the one that exists on master switch. So a copy of configuration file from master switch is given to every switch in the stack. And this is exactly the positive side of the story with stackwise technology. Because from administrators' point of views, we can add or we can remove switches without any interruption. So adding new switches or removing old switches without interrupting the service is what we are always looking for. You do not even need to configure this newcomer, this new switch that you're going to add. Stackwise will take care of that for you. So the Stacks master or the master switch is going to auto configure the new arrival with the Stacks iOS image. As I said, one iOS image, let's call it Stacks iOS image, is shared between all switches on the stack, and it's the job of master switch to auto configure the new arrival or newcomer switch with the Stacks iOS image. As you can imagine from this technology, the merit is that we are not going to have any single point of failure anymore, because any old switch can crash, and thanks to Stackwise we don't notice that. There is no interruption to the service in the production environment. Our network operates well, so no single point of failure in switch stack. But there is a single point of pain, as they call it. If one of our cables breaks, we take quite heat in capacity, and some say we take a 50% heat in capacity. So we have that. However, the failure takes literally microseconds. So 50% cut in service is very, very short. So it's very, very temporary. And this is thanks to NSF technology that is supported in Stackwise. We talk about NSF more. Non-stop forwarding NSF is supported in Stackwise, which helps keep the packets flowing when there is even a slight break in service, such as when master switch in Stackwise technology goes down, another switch needs to be chosen and take over. With Stackwise, NSF works with what we know as RPR plus. I go through that in more details in the next slide. To keep things rolling, NSF works with RPR plus in Stackwise, and we are cutting over from one master to another thanks to NSF employment into the Stackwise technology.
Stackwise image is very, very important. In fact, they say Stackwise image is everything here. So let's talk about it and see why it is indeed everything. This is because Stackwise requires every switch in the stack to run the same iOS. So this is the precondition. Therefore, it is highly recommended that Stack members have the same feature set. And what we mean by same feature set, we want all members of Stack to be either IP services or IP base. What are the differences between IP base and IP services? IP base is for the standard multi-layer software image, or SMIS for standard switches, and IP services on the other hand, this image is for enhanced standard multi-layer switch image, or EMI switches in Cisco iOS. EMI, or enhanced one, is for iOS software releases after 12.2. So later iOS versions, they support IP services. But once again, our precondition is that Stackwise asks you to have the same feature set on all Stack members. And by feature set, we mean they all have to be either IP services or IP base. Let's see IP base and IP services in more details. For Catalyst 3750 and 3560 switches, for Cisco iOS software release earlier than 12.2, we refer to the image that provides layer 2 features plus basic layer 3 routing as the standard multi-layer image, or SMI. So SMI, or standard multi-layer image, it provides layer 2 features and basic layer 3 routing. However, image that provides full layer 3 routing and advanced services is referred to as EMI, or enhanced multi-layer image. So with EMI we expect full layer 3 routing and advanced services, whereas with SMI it provides basic layer 2 and basic layer 3. The inter-VLAN routing, this is one of the features that is supported on both IP base or SMI, as well as IP services or EMI. So inter-VLAN routing feature is supported on both. When I'm talking about IP base feature set, this includes advanced quality of service, rate limiting, access control list, and basic static and routing information protocol RIP protocol functions. So basic layer 3 routing is supported with IP base feature set. Dynamic IP routing protocols like OSPF, Open Shortest Path First, BGP Border Gateway Protocol version 4, Enhanced Interior Gateway Routing Protocol EIGRP are available only on the IP services image. This is important. I'm aware of the exception that we have with EIGRP that is supported in IP base, but that one is only EIGRP stop, which means that this software will be the last software connected to the EIGRP topology to the rest of the network. Apart from that, all these advanced routing protocols, they are only supported on IP service image. OSPF
it has very basic support with IP base, but the advanced features they are all supported only with IP services. The IP services image provides therefore a richer set of enterprise class features, which includes advanced hardware based IP unicast and IP multicast routing. So, advanced hardware based routing, be it unicast, be it multicast, they are supported by IP services. This is the distinction between these two feature sets. IP services also support IPv6 layer 3 switching in hardware. So remember, with advanced IP services image feature set that I'm talking about, the support for unicast and multicast routing is in hardware, is provided by hardware that is preferred over software. Also, its support for IPv6 layer 3 switching is in hardware again, that is preferable over software. For IPv6 layer 3 switching to be supported in hardware, we need the addition of the advanced IP services license, and that can be added also to IP base as well as IP services image, but that's beyond the scope of our discussion here. And the final point about these two SMI versus EMI, remember, both the IP base image as well as the IP services image, they allow for layer 3 and layer 4 lookups for quality of service and security purposes. Next, we want to see why having the same iOS image is important. The important scenario for this is when we are going to add a new switch to the stack. What happens is that the master switch is going to ask you whether or not the newcomer has the same iOS image as other stack members. You don't need to configure a switch to add it to stack. Remember that. And this is because the master switch here is going to take care of that for you. And therefore, adding a switch, master needs to know if the newcomer, if it's running the same iOS image as the master. If yes, then master, all he needs to do is to just send configuration file to this newcomer, to this new switch, and things will move forward from there. However, if new switch does not have the same iOS image, then one of these conditions should happen. First, master switch downloads iOS from its own flash to newcomer, to new switch, and then sends configuration to this newcomer, and new switch finally joins the stack. Secondly, we have the option to configure a TFTP server for that specific iOS download purpose. The iOS that is supported on a master switch and is run by master switch. And then master grabs iOS from TFTP server and sends it to the new switch, to newcomer. And then it sends the configuration over, and new switch will join the stack successfully. These first and second scenarios, they have one assumption. So these two possibilities, they assume that newcomer or new switch's hardware can handle master switch's iOS image. If not, master will put newcomer new switch into suspension and warns admins that master expects to be supplied with an iOS image that supports the master's hardware as well as the new switch's hardware. So master will upgrade every switch that was already part of the stack to that iOS along with the new switch newcomer, and then entire stack goes live. The order that I explained here is a bit different from what you see in the slide. So I've put first when master's hardware is not the same as the newcomer. And in that case, we need to warn the admins.